Welcome guys, this is our lesson number 2. We'll be looking at work done by non-conservative force or forces depending on how many they are. Now if you still remember, earlier we did mention that forces can be classified into conservative and non-conservative. Now with conservative, I think we had an agreement that conservative force in this study of work, energy and power, will be looking at force of gravity. Now all the other forces that you can think of will therefore be non-conservative forces, e.g. your friction, your applied force, your tension and other forces. So they will be examples of conservative forces. Now earlier we're talking about conservation or the principle of conservation of mechanical energy, whereby we said the total mechanical energy of an isolated system is conserved. Isolated, I think I left out D. So is conserved, meaning if you have an object like the scenario we had earlier, then if there is only one force acting, and which is the force of gravity, and upon the motion of the object between any 2 points where you'd be checking, now maybe the energy present, the energy must always remain constant. That means energy between any 2 points must be equal. Alright, now I think we said this scenario or this equation or this principle will only apply it when there is only one force acting, which is force of gravity. And now what happens if there are other forces like friction? Let's take this very same scenario, for instance. Let's take this very same scenario. We can just let's just copy this diagram just to save time. Let's copy this diagram. It will save us time. All right. We need to copy. Okay. Then we paste. All right. Let's remove what we do not need so that we'll start our discussion. All right, you can keep that. Now let's say this is an object which is falling. Now while the object is falling, let's say now, let me just remove this closed box now, which will therefore imply that now the system is no longer closed. So it means there will be other forces acting on the system other than the force of gravity in addition to force of gravity. So let's say for example, as the object falls down, there is a force of gravity, force of friction in terms of air friction. Now let's say now we're saying air friction is not ignored. So meaning there will be force of gravity as the object falls. If you can think of the free body diagram, there will be downwards force of gravity. Then in the upward direction, there will be frictional force due to air. Now, earlier, I think we had an agreement that if you look at this scenario here, at the top, you will have kinetic energy equal to 0 because the object is dropped. So the object will not be moving. So kinetic energy will be 0. But because it is at its maximum height relative to the ground, so it would mean then the potential energy there must be at its maximum. Now, if you think of its potential energy when it falls down, the height decreases. Now, if the height decreases, it would therefore mean the potential energy must decrease up until the height here, as we discussed before. The height is equal to 0 meters. So mgh, the potential energy must therefore be equal to 0. P equals to mgh. Now, if the height here is 0, so it means your EP will be 0 joules here. So potential energy is equal to 0 joules. But then if you think of kinetic energy now, which is your half, mv squared, that is your ek. Now, as the object starts from rest, as it goes down, it picks up speed. So the velocity increases. So it means kinetic energy is going to increase from 0 to maximum, according to our discussion earlier. And we ended up having this equation, which said EP, rather EM, at the top is equal to EM at the bottom. Now, this is what we discussed earlier, where there was no air resistance. Now, I need us to come up with a certain notation. Let's say here, let's call this our point A, the point of departure. Then we'll call this point B, where it reaches the ground. Now, your ground will be point B. Then where it started, you'll be having a point A. So meaning we can just change the top and bottom here to A and B. Okay, to erase here. All right. Now let's change here. Say at the top we have A and we have B. Remember, this is without friction. What if now there is friction with a friction involved? All right. Now, I think I need to highlight this one. Okay, it is going to change color. It's fine. All right. Now, if there is air friction involved, then what happens? Now, we need to think about it. Sorry. Remember, according to energy principles, resistance of friction, it decreases the energy of an object. It takes out energy from the system. So it would therefore mean that if you think of here, your EM, that is at point A, EM at point A, and your EM at point B. EM at point A and EM at point B. Now we can just write EM at point B. Now they will no longer be equal for sure, because air resistance decreases this energy. So it means here, if you had started with your maximum potential energy, not all the potential energy here will be converted to kinetic energy. Some energy will be lost will be taken out of the system due to this friction. Now it would mean then the mechanical energy at point A will be bigger than energy at B. I hope you get that. Why are we saying it is bigger? Here at A, the object hasn't moved, it has not experienced any air resistance. It is going to experience air resistance as it falls. Remember, this air resistance, we can refer to it as friction. Friction opposes motion. So while the object is still at A, it has not moved, so it will experience no friction. Then it begins to experience the friction as it falls down. So when it gets to the ground, it would have lost some of the energy it started with here due to air resistance. So what we need to think about now is the fact that our mechanical energy is given by EP. Then here, because the motion started at point A, we can just write this is potential energy initial plus kinetic energy initial is greater than potential energy final. Why final? Because it started at A and it ended up at B. So at B, you're going to have your final, that is plus EP final. So this is the situation we are at now. So now what we need to think of now is how do we make now this equation equal again? How do we ensure that this energy at A is equal to energy at B? So it would mean then we need to think about the work done, the energy which is taken out of the system due to this force of friction or frictional force. So if you notice this, we're saying at A, that is initially, the energy is bigger than the energy at B, that is finally. And excuse me, if you remember very well, when we're calculating or when we're talking about work done, that is, we're saying it is the energy transferred. Such bar energy can be transferred into, that means a positive work is done, or energy can be transferred out of, that is a negative work done. So in other words, you would understand that if the object is falling downwards, frictional force will be acting in the opposite direction at an angle of 180 degrees. So it means it is doing a negative work. It is taking out energy from the system. So what we would rather do here is to say, okay, now that here we have our energy initially, which is bigger, let's bring in this work done by friction. If you have noticed here, I've noted that this work done by non-conservative force will be represented or denoted by WNCW for work done, then NC for non-conservative force. So we need to bring in this NC now, WNC. In other words, what we're saying here, never mind that I've substituted a positive, because anyway, when you calculate the work done, you do not even include the signs, because the signs will come in as a result. In fact, just show in which direction is it acting using the angle. So you can just substitute your positive here, it's fine. So it will no longer be bigger, because this one is the energy which is taken out. You need to take note of that. This energy is the energy which is out. That is, this is your negative work done. Negative work done. So you need to note that. So in other words, we're saying the energy we had before, we're reducing it. We're decreasing it now because it was bigger. Then once you bring this WNC, it means we are decreasing the energy. So that now the two, that is mechanical energy at A, will be equal to mechanical energy at B. That is, initial energy must be equal to the energy finally. So you can now take down P F. Remember, okay, your P must be a small letter, I suppose, plus E P, rather EK now. I made a mistake. Should be EP EK. Let me correct this. So it should be EP EK. Okay. Now I hope you get this. Let me just explain this once more. Here, energy at A is bigger than energy at B. One would probably ask why. At A, it has not moved yet. It has the maximum potential energy, but as soon as it starts moving, it experiences resistance due to air, that is frictional force, is acting now. So the frictional force takes out energy from this object, so that when it gets to B, the energy it started with has decreased as a result of the frictional force. Now we're saying to make this the energy at A, or mechanical energy at A, equal to mechanical energy at B, let's bring in this WNC, work done by frictional force, which is your non-conservative force. So we're saying plus, not that we're increasing it. You know that frictional force is acting in the opposite direction. We do not substitute the negative signs here. The direction, remember, in science or in physics, negative would be showing in which direction is it acting. So here the direction is denoted by the angle, so you do not need to think of signs. You can just write positive. So WNC now is the work done, the energy taken by friction from this energy you started with. So that if you are decreasing it now, it will be equal to that one we're saying it is smaller. All right. Now let's rearrange our formula so that formula at the end. Now You can just keep your WNC as the subject. So it would mean then that we have EPF, this one. Then you take this I to the other side of the equal sign, and a figure a change is sign. You have EP I, then plus EKF, KF. Then you take this EKI to the other side, you have EKI. Now, I think you can appreciate the fact that this is change in potential energy, because remember, change is final minus initial. So it means you have change in EP plus, again, this is change in kinetic energy, because you have kinetic energy final minus kinetic energy initial. So final minus initial gives you a change. So this is change in K, which is equal to WNC. There you are. We have a new formula that we will use when we are working with now cases where there are non-conservative forces acting in the system. Now, let's take this example. All right, not this one. For it. All right. So is our example there. Okay, we need to paste it here. All right. So we're going to see how this formula works now. Here it says a skateboarder with a mass of 65 kilograms skates down a slope from point X to point Y while experiencing a frictional force of 150 newtons. Point X is 3 meters above the ground level. The speed of the skateboarder at point X is 1 meter per second, and his speed at the bottom is at the bottom of the slope Y is 4 meters per second. Use energy principles to calculate the work done on the skateboarder by friction. Now, you need to take note of the fact that friction now, unlike force of gravity, is a non-conservative force. So in other words, it means we need to work out how much work is done by this non-conservative force. So remember our formula, we said it goes WNC is equal to change in EP plus change in EK. Now this formula, unlike the formula for principle of conservation of mechanical energy, that is Emec at top equals Emec at bottom, the formula for mechanical energy or for conservation of mechanical energy will not be given in the exam, but this one, it will be there in the answer sheet, so you do not need to worry much. So the question here needs us to work out the work done by friction. So it means we are required to find this WNC. Let's see if we have enough information to work it out on this other side. So if we expand this formula, maybe it will help us. We have MGH, remember, change will be final minus initial. Remember, this is your potential energy plus half mv F squared minus half mv I squared. All right. Now let's see. Okay, space now is gonna be a bit of a problem. Okay. Now, are we given a mass? Yes, the mass is given. Are we given height? Yes, the height is given as 3 meters above the ground. Remember, your height must be vertical height work done by force of gravity or gravitational potential energy. You always take the vertical height. So, and now, if we move to the side of the kinetic energy, we're given both speed and mass. So we can just go straight and substitute. Mass is 65. Mass is 65. Then into 9,8 into, now your vertical height is 3. All right, I think I've just committed a minor mistake because here we need to be very careful of the fact that we are having final and initial. So I think our initial, because the skateboarder skates down, so the border starts at A initially and final will be at Y. So it means our final here, the potential energy will be 0. All right, let me use minus, not plus. The potential energy will be 0, y 0, because here your height is equal to 0 because you're on the ground. So if you substitute 0 here, you get 0. Then minus 65 times 9,8 times 3 plus now here we have half m, your m, that is mass, is 65. Then b, now what is your final velocity? If the skateboarder started here with 1 meters per second, finally he'll be moving with a speed of 4 meters per second. Then you square it, then you say minus half into 65 into 1 squared. All right, remember we had our WNC equals to, then we can just go straight and use our calculator without any worry. So you have 0 minus 65. All right, let's try and substitute use our calculator. Now we punch it as it is. Then we have 3 plus 1 over 2 into 65 into 4 squared minus 1 over 2 into 65 into 1 squared, right? Then we get negative 1423, negative 1423, comma, calculator now, okay, comma 5. Now remember, the instruction is always round to the minimum or to a minimum of 2 decimal places. So if you write 0.5, it becomes an incorrect according to the instruction. So we need to write 5 not. Then we write our units. So because this is just a scalar, we can leave it as a negative answer. Otherwise, if it was a vector, you write as a positive answer and you write the direction. So here, this is the work done by frictional force, and you can see it is negative because friction takes out energy from the system. All right, I will leave 1.2 to you. Please attempt 1.2.